and Engineering in National Institute of Technology, Rourkela, for over 5 years before joining IIST Shibpur. She is currently an assistant professor in the Department of Information Technology, Indian Institute of Engineering Science and Technology, Shibpur, India. She has published her research works in several international journals, conferences, and book chapters. With immense pleasure, I would request Dr. Ruchira Nashkar ma'am to please come on dais. Over to you, ma'am.
Thank you, Tanushree, for the nice introduction. So I welcome you all to the first technical session of this conference, where we shall be having 4 technical papers, contributory papers. The first paper is on a cellular automata-based clustering technique for high-dimensional data. So I welcome the authors. Please.
Am I audible? Yeah. Good afternoon. My name is Abhishek and I'm from NIT Trichy and I'm here to present to you my research work titled A Cellular Automata Based Clustering Technique for High Dimensional Data. So in today's presentation, I'll just give a brief introduction as to what clustering is, how Okay, I'll start again. So good afternoon. My name is Abhishek and I'm from NIT Trichy and I'm here to present to you my research work titled A Cellular Automata Based Clustering Technique for High Dimensional Data. So in today's talk, I'll just give a brief introduction as to what clustering is, how we can use cellular automata for clustering, some of the limitations of existing algorithms and what we have tried to do in order to overcome that, and our algorithm itself. So yeah, let's begin. So in simple terms, clustering is dividing data, unlabeled data, into groups or clusters as we call them, such that the data within each cluster is as similar as possible and the data across 2 different clusters are as distinct or as different as possible. So in mathematical terms, we tend to express this in the form of distance. We say the data between the data that is part of a single cluster are similar. So we say that it has less intra-cluster distance, and the data elements across 2 different clusters, we say they have large inter-cluster distances. So one thing to note here is that at any point of time, an element can only be part of one cluster. Hence, we can represent it in the form of bijective function, say f, between set of the objects that are to be clustered, where a relation R partitions these objects into segments or clusters, right? Another thing to keep in mind is that the relation R, which is dependent on the bijective function f, that determines the type of cluster, the clusters that are being formed. So it is important that we choose the right bijective function f that will give us the best possible cluster. So in this regard, we have reversible finite cellular automata with its inherent bijective global transition function, has been proven to act as a clustering tool. Yeah. So every configuration of a reversible cellular automata, it belongs to a single cycle, and the configurations that belong to the same cycle essentially belong to the same cluster. So we say that two configurations are close to each other if they are reachable from one another. So, and all reachable configurations together form cycles. Mathematically, we say configuration B is reachable from configuration A if there exists a function f such that f of A equals B. And since we're dealing with reversible cellular automata here, at some point of time, f of B is also equal to f of A, since it's cyclic. So here are some of the limitations to existing algorithms. First and foremost is due to the inherent hardness of reversible cellular automata. For any R radius CA, there exists only a small number of reversible CAs, and even amongst them, not all of them are suitable for clustering. Since our target is to maintain less intra-cluster and large inter-cluster distance, we'll have to pick our CAs carefully. And second and most importantly, as we consider the cycles of CA as our clusters, in the worst case scenario, we may have to explore all the possible configurations. So for a CA of size n, say 2 state, then we'll have to explore 2 per n total possible configurations. And this is infeasible for high dimensional data. Yeah. So for this research work, we have considered one-dimensional n-cell, two-state radius 2 cellular automata under the null boundary condition. So this means that for any particular cell, there are 2 cells to its left and 2 cells to its right. We call it as the neighbors. And these cells, they change their state on the application of a mathematical function or a rule, right? So we have represented this rule in the form of a binary string. So you can see in the PPT there, the rule number 2605, whatever, has been represented in the form of a binary string. Yeah. In order to benchmark our algorithm, we have considered 3 performance metrics: silhouette score, Davis-Bouldin score, and Kalinsky-Harabaz index. And we have benchmarked it against search algorithm, DB scan, mean shift, etc. So as I mentioned before, selecting the right bijective function is important. So that translates to selecting the proper rules. So in case of R equals 2, that is radius 2, which is what we have taken, there are only 226 possible CA rules which are reversible, and our target is to select those which have a strict locality property. So we do this because we want to maintain that less intra-cluster distance. And we define the strict locality as less number of changes between consecutive configurations. So in this case, only similar objects are put together, and we represent this mathematically in the, by rate of information flow. So to measure this rate of information flow, we observe the change in state in rules corresponding to its adjacent neighbors. We represent this in the form of a percentage that lies between 0 and 100%. So in the example there, we have the leftmost cell, 0, and if you apply a rule, its value changes to 1, but the overall value remains same. So this means that the change in value for that particular cell, the change in state for that particular cell, it does not affect the next neighbor. So that equals that the rate of information flow for that particular cell is 0. So we have chosen arbitrary conditions to help us filter out some of the unnecessary reversible CA rules. Our criteria being the rate of information flow for the 2 left and 2 right should be less than or equal to 75%. So that brings down from 226 reversible CA rules to 160 rules. So in order to explain the algorithm, I've shown you the data set here, and I'll explain it with pictures as we move on. So the data set that we have used is, it has the statistics of IPL players for the year 2018, and our target is to cluster this data set. Yeah, so now this brings us to the first step of algorithm. Since the CA is not capable of processing real valued data, we first have to convert it to something that the CA can handle, right? So what we have proposed is we have proposed a 2-bit binary frequency-based encoding that maintains minimum Hamming distance. So we'll iterate through each attribute, and I'll show that second. So yeah, so what we do for each particular data point, we calculate the frequency of the values, and then we arrange it in ascending order, and then we encode the first m by 4 with 0, 0, second m by 4 with 0, 1, third with 1, 1, fourth with 1, 0. So here we can see that it maintains minimum Hamming distance, and it uses 2-bit frequency-based encoding. So this is how the dataset looks after we have encoded it. So it's just a bunch of binary strings, 2-bit strings. Yeah. So the next step we have taken in order to tackle the high-dimensional data clustering inefficiency is we have decided to vertically split the dataset before we cluster. So what this does is, say you have a data set with say n features, right? N dimensions. We'll divide those n n features into 2 different or n number of splits, and then we'll apply our clustering algorithm to each of the split parallelly. So yeah, this is because for, let's say, the entire data set, we get an n-bit CA, then in order to explore all the possible configurations, we'll have to explore 2 power n possible configurations. But in the example in the PPT, if you're dividing it into, say, n1 and n2, then we'll have to explore just 2 power n1 plus 2 power n2 configurations, which is comparatively less than the overall. So one thing to note here is that when we are vertically splitting this data set, we have used 2-bit encoding for each of the cell. So it is important that we do not take half a feature into a particular split. So the split size will always be even number in our algorithm. So our data set had 24 dimensions and 2 bits, that's 24 into 2, 48 bits. We have just divided it into 5 or 6 splits equally. Yeah. Yeah, so now we move on to the clustering part. This is stage 1 of clustering. We consider each vertical split separately, and we run the clustering algorithm in parallel. So what we do is we apply a CA rule to the initial configuration, say 0, 0 cell or, of the data set, and that will give us the next configuration. And if we apply the same rule to that configuration, that will give us the next configuration, and so on. Since it's reversible CA, at one point of time, we'll get back the original configuration, and that will be our first cycle or first cluster. So from the remaining configurations, we use the same rule to get the other clusters. And then we, depending upon the number of clusters that are being formed, we encode each cluster using binary encoding again. So what we do essentially is, let's say we end up with 4 clusters at the end of this stage for the first vertical split. We'll use 2-bit encoding. So we'll name the first cluster as 0, 0, second as 0, 1, 1, 0, 1, 1, etc. In this way, we are reducing the length of the configuration without losing the data, since we are using reversible form of encoding. So yeah, this is just a pictorial representation. Let's say the first, when you apply our rule, the first configuration, it results in the next state, that is C. So A and C will belong to the same cluster, and B will be a separate cluster if, yeah. And now that the stage 1 clustering is over, we move on to stage 2 clustering. So at this point, we concatenate the strings, the encoded modified configurations from each of the vertical split. So that will give us the entire encoded string. and we apply a different rule to this modified configuration until all the configurations are part of some cycle. So one thing to note here is that at no point of time we are dealing with the number of clusters. So the number of clusters that we end up with at the end of stage 2 may not be our desired. Sorry. Okay, so may not be our desired number of cluster. So in case 1, when we end up with more clusters than we need, what we do is we break the cluster with the least number of elements, and then we attach it to one of the other remaining clusters based on silhouette score. So the cluster which gives the maximum silhouette score, we attach it to that cluster, and we do the same until iteratively, until we can reduce from k clusters to k minus 1 clusters to k minus 2, so on, till our desired number. So in the other case, when we end up with less clusters than we need, then we apply a different rule at stage 1 and at stage 2, and we get an auxiliary cluster. So if this auxiliary cluster has the same number of clusters we need, then we report that as our value. And if it doesn't, if it has more, then we apply the previous like stage 1, the case 1 clustering, getting desired number. If it doesn't, then we keep applying different rule until we get the auxiliary cluster which has more or less or equal. Yeah, so this brings us to the last part, which is to decode our encoded configuration. So initially when we are encoding it, we are saving the encoded strings in a hash set, a dictionary. So for fetching the original value back is not a hassle, so we can just decode it directly. So this was our result for desired number of cluster being 2. We can see 2 different lists of players. Yeah, so results and analysis. At different points of time, we were faced with an option of using the same or different CA rules. For example, in the vertical splits, we found that using the same rule for each of the vertical split gave us the best possible result. And in case of difference between the rule used in stage 1 and stage 2, we found that using a different rule in stage 1 and stage 2 gave us better results. So essentially, we deal with 2 rules, rule couple, one rule in stage 1 and one rule in stage 2. As far as time complexity is concerned, the maximum time taken in the algorithm is in stage 3 when we have more than the desired number of clusters. So what we do, we have calculated to be m cubed by L, where m is the number of data points in the data set and L is the size of the vertical split. So this way, there is no dependency on the number of features or number of dimensions in the data set. So we are able to counter that part. Here's a performance analysis benchmarked against for four data sets against the popular algorithms. Our algorithm performs comparable to k-means for the first data set and better than the other algorithms for that data set. And for the remaining data sets, it performs as good as all the algorithms. As far as future work is concerned, right now we have just used uniform CA, which limits the sample space of CA rules that we have. So in case we use non-uniform CA, we'll have more number of rules to work with, and that gives us the possibility of getting better results. And also, we could probably characterize the CA rules that we have used in order to further fine-tune and improve our clustering quality. Probably based on some parameter like the length of cycle formed or something like that. And I've put the acknowledgements on the slide. Thank you to all who have been huge guidance, without whom this project would not be possible. And that's our base paper and other references that we have used. And that concludes my presentations. Is there any questions or any suggestions also you have that we can probably implement?
So I have a question. This study is pretty interesting. but how did you encode the elements of an
Hello,
individual
Abhishek.
attribute?
Good presentation. Hello, Abhishek.
Hi.
It's a good presentation. I have only one simple question.
Okay.
That you use the reversible rules, na? Reversible CA.
Yeah.
So there is total 62 rules which are used to generate the reversible CA. So how many rules you used in this particular application?
Around 160 rules. We tried all possible combinations, which will give us the best result.
Radius 1. I talking about the radius 1.
We have used radius 2.
Radius 2.
Yeah,
Achha,
so
for
that.
radius 2, you use the 160.
No,
How
so
many
radius
rules?
2 totally has 226 reversible
226,
rules,
na? Okay.
out of which our criteria to meet the clustering criteria, we used 162 rules.
That's all.
Yeah.
Okay.
Thank you. Any other questions?
Yes, so Abhishek, I have one question. Have you categorized the features? That means whether continuous or discrete, what I try to say, qualitative or quantitative. Have you categorized on that, or any kind of
No,
features?
just numerical data, continuous.
Continuous attributes.
Discrete value, sorry, yeah.
Discrete.
Yeah.
I want to ask whether it is qualitative attribute or quantitative.
Quantitative. So we, if you see, we
Okay.
had removed the names of the players, which we can't cluster.
Okay, so that
So-
means you have not done the experimentation using qualitative attribute.
Not yet.
Okay, thank you.
That's a good idea, actually. Thank you.
Have you tested your data on other sets other than one particular?
Sorry.
Have you tested your data on other data? You know, some.
Yeah, so we have tested with 4 data sets. So we have the IPL data set. We've tested with school district breakdown. Iris is a common data set that we have used, and body move. So one thing that I forgot to mention is, in case we don't have high dimensional data, that is if there are data sets with less number of features, we can skip the stage 1 clustering itself entirely. So that will save us some computational time, and it will still give us good results. We can use stage 1 and stage 2 for those data sets which have high number of features.
Sorry, there was a question about possible suggestions. So, I think one very interesting question of wide usage is classification of biological data. So you can start with grouping animals into classes and see if that matches with the conventional classification schemes. You know, just take some data like all kinds of animals and then use your algorithm to classify them into something or the other and see if it agrees with the usual zoological classification scheme.
Thank you.
So maybe you will be having more questions, so we can take further questions offline. So we have the other authors, second paper. Thank you, Abhishek. The next paper is on cellular automata based sentiment analysis. I think it will be an online presentation. So the next presentation will be online. So the author will be joining us remotely.
Yes, ma'am.
Is the author there with us? There with us.
Yes, sir.
Okay.
Hello, ma'am. Am I audible?
Yes, you are audible.
Yes, ma'am. Good evening, all of you. Today I am going to present my research work, that is cellular automata based sentiment analysis. The outline of the presentation is as follows. First, we have to go into introduction part, then related work on sentiment analysis, then elementary cellular automata, details of elementary cellular automata, then proposed methodology, which includes block diagram of the proposed model, then different modules, then algorithm for training process, then results and performance analysis, finally conclusion of the paper. So before moving to the introduction part, I would like to say something about NLP. We know that NLP is natural language processing, and it is branch of artificial intelligence, which deals with the interaction between human and machine using some natural languages. So the main objective of natural language processing is to read, decipher, and understand and make sense of human language in a manner that is valuable. There is a collection of fundamental tasks in NLP. For example, topic modeling or language modeling, then question answering, information extraction, and so on. So, in order to solve all these problems, we have to understand the linguistic properties of the languages. So here, first we have to go through the linguistic properties, that is low-level linguistic properties and high-level linguistic properties. Low-level linguistic properties include characters, words, stems, and parts of speech tags, and its phrases and structures. And high-level linguistic properties means syntax and semantics of the language, the dependency between syntax and semantics. And also some other kind of properties are structural properties, which includes the layout of the word. That means whether it is bold or italics or underlined. Such kind of properties that we have to analyze in order to solve the fundamental tasks of NLP. So it is not that much easy to extract all such features from the languages. So in this scenario, we are thinking about CA-based language independent generic ML machine learning model for solving a task. So we have taken a problem that is sentiment analysis, and this problem is solved by using cellular automata with the development of machine learning model. So sentiment means it is an attitude or emotion or mood of a person in the form of text. Or we can say that we can use this sentiment analysis in order to identify the polarity of text and the emotions of a particular topic in a sentence. And also it is used to identify the emotion of the body of emotion behind the body of the text. That means we can categorize the text into positive sentiment or negative sentiment or neutral, like that. So this classification is done by using some machine learning models in normal in common scenario. But here what we are going to do means we are using cellular automata for generating cycle values, and
Hello,
by using that.
hello,
Hello.
Elizabeth.
Yes, ma'am.
Sorry to interrupt you. Can you please make your screen a full screen?
Is it visible, ma'am?
Yes, yes, yes. This is fine, I think. Is it visible now? Okay. Thank you.
Okay, ma'am.
Please continue.
Yeah. So to solve this problem, there are so many different sentiment analysis tools are available, but all the tools are dependent on its language and based on the linguistic properties of the human language. And this sentiment analysis is also very important in this nowadays, because it is an ongoing research field of text mining. So the related work on sentiment analysis, actually Giuseppe et al. Developed different models using some APIs, Google Natural Language API, Python Natural Language Toolkits, and Paladots. And their study reveals that each sentiment, affect, emotion, opinion, everything are different concepts. So we have to we need different kinds of tools and matrices for analyzing the dimensionality of an opinion. And Hossein et al. Worked on sentiment analysis using deep learning algorithms. They used CNN for extracting low-level features and LSTM for extracting high-level features. And they worked on Bengali language, and they got testing accuracies around 75%. Then Yadalai and co-workers done a work, a survey. They have done a survey and proposed the taxonomy of sentiment analysis. They categorized the entire sentiments into two classes. One is opinions, other one is emotion. If the text belongs to opinion, then they are categorized that one to neutral, positive or negative. If it is emotion, then love, fear, anger. These are the different classes. And Gautam et al. Proposed a model, and Govindarajan also proposed a model. These two models are based on machine learning algorithms. They used naive-Bayes and support vector machine and maximum entropy algorithms. And their work also based on the linguistic properties. So here we are going to use elementary cellular automata, and we know that elementary cellular automata is the simplest form of CA. Here there are three cells are there, current cell and left and right cells. Then two states, 0 and 1, 0 or 1. So the next state of the cell is updated by using the present state of that cell as well as the present states of the neighboring cells. So that can be represented mathematically using this equation 1. Here there are three cells, so possible states 7 states 0 to 7, that is 8 states are there, 2 raised to 3 8. Then the next state will be based on the rules applied for each cell. So the block diagram of our model is this one. Here the input text is pre-processed. Then by using that pre-processed text and its corresponding ASCII values will generate a rule vector table, and these rule vectors are given to cellular automata along with the evolution steps and number of repetitions. Then we will get some cycle length values from the cellular automata, and these cycle length values are used for extracting certain features. Features are two types are there. One is filtering features and other one is prediction features. After after calculating all these features, we will apply prediction algorithm for getting the test labels. Finally, we will analyze the performance of the system in the form of F1 score, precision, recall, and accuracy. And this proposed model is CML, Cellular Automata based machine learning model. And there are 4 different modules, just we divided into 4 modules. First module is text to rule vector conversion, then cycle length value generation, then feature extraction, then prediction. So module 1, for example, here how we convert a text into corresponding rule vectors. So in order to, for example, too bad, this is one negative sentiment. And this sentiment is first we have to convert it to vector form. In order to get vector form of this text, we have to use the ASCII values of the input text. That means ASCII values of the each letter. So these are the ASCII values of the corresponding letters, space and dot, everything will be considered here. So we will get rule vectors like this. These rule vectors are used as input for CA. So CA, here we are using one-dimensional elementary cellular automata, and the next state of the current cell is obtained by applying these rules. Here each these values are acting as a rule for that particular cell. So the CA will evolve 1000 times. The value 1000 is taken based on the length of the text. That means if the evolution step, which is equal to half of the maximum length of the text, that value is taken as evolution steps. Then after certain iterations, the pattern starts repeating. Then the length of the pattern is taken as cycle length value. If the pattern is repeated at least 32 times. This is just a threshold values taken. Then if there is no repeated pattern at all, then we will assign 0 or some other negative numbers. The evolution process looks like this. Initially, we are assigning the initial state of the cell, that is zeros and ones, alternate zeros and ones are given initially. Then the processing takes place based on the role of the each cell. Then if the pattern, for example, in the first column, you can see 110, 110, 110. So the length of the repeated pattern here, it is 3. So cycle length value for this cell is 3. And for the next second column, there is no repeated patterns at all. So we will assign 0 or some negative number. And in the here fourth column, you can see 0, 1, 0, 1, 0, 1. So the cycle length value of this cell is 2. So finally, for example, if the text is this one, then after CA evolution, we will get cycle length values like this. And these values are plotted like this. So we'll get CL graph for text 1 like this. And by this is for another text. Here the CL values like this and the graphs looks like this. So then what we should do means, after getting this graph, we have to analyze the graph, and by analyzing, we have to extract certain features from the graph. For example, here you can see only one maximum cycle length value, or only one signal you can see. And in this case here, 2 MCLs are there. Like that, we have to analyze each graph and find out, we have to extract certain features. And the features what we are using here, it is, first one is maximum cycle length. That is maximum value of the CL values. For example, text 1, it is 14. Here you can see this is 14. Here only 14 is there. So this is the maximum CL value, that is MCL. And the values less than MCL and greater than a certain threshold, that values are taken as next to MCL value, that is NMCL values. And how many MCLs are there, that is MCL count, that is 1 for text 1. Then some other features, that is right step, right fork, and left fork flags. These are the 4 flags as per the MCL. See, here you can see in the text 1 graph, one MCL point, only one MCL value is there, and right side you can see step-like signal, and left side of this MCL you can see one left fork signal. So for this graph, RSS will be set to right step signal, RSS is set to 1, and left fork LF also set to 1. All other will be set to 0. Like this, we will set all these 4 flags. Then any negative values, that means there is no repetition, then the value will be negative. If it is there, then this flag will be set to 1, otherwise it is 0. Then another parameter is group value. Group value also assigned based on the MCL and NMCL. Here, if we apply this, that is MCL minus maximum NMCL, which is less than or equal to 20% MCL, then that reviews are categorized into group 0. If MCL count is equal to 1, then group 1. If it is greater than 1, then group 2. Then another one is signal location vectors. This is another parameter. This is extracted from the graph itself. If we know that the MCL location of 14 is 57 and NMCL locations, the corresponding values are 55 like this, then the SLV, signal location vectors, are taken like this, 55, 61. For this MCL, all the NMCLs are included in the SLV. If more than one MCL locations, then the present which MCL location we will consider, that value we will not take. All other MCL and NMCL will be there in the SLV list. And this SLV list is used for finding signal distance vectors. And signal distance vector that's the difference or distance between MCL and MCL location and SLV. That means SLV contains all the MCL locations as well as NMCL locations. Then we have to find the difference between MCL location and NMCL locations. So these values 55 minus 57 minus 55 2, then for like this we will find the distance between. Then we will categorize it into two: left distance signal distance vector and right signal distance vector, so that we will get values. We will get two lists: one is leftmost, another one is right side, as based on the MCL location. Here it is 57 MCL location. So 57 comes between 55 and 61. So the values left to 57 is taken to LSDB, and the values right to 57 is taken in the right SDB. So all these are filtering parameters. That means in order to make some clusterings, we will use these parameters. And for prediction purpose, again, three more parameters are used. One is cosine similarity index. And the fundamental equation is used for finding cosine similarity between CL values of the testing and training data and Euclidean distance. That also on the same fundamental equation is used for finding distance between CL values. Then prediction R value, relation between testing and training data by taking the ratio between matched signal pair and mismatch count. That means in SLV and LSDB and RSDB, some values are there. That each value is taken D1 and D2. Then we will, if both are same, means the signals are matching signals. So that value will be 1. Otherwise, so here we are using not the exact similarity, but if the ratio is greater than 0.8, that means 85%, more than 85%, then that values are taken as matched signal pairs, other values are taken as mismatched. Then after identifying all the MSP and MMC, we will take the ratio, that is the R value of that particular test data with respect to all the training data. Then we will use algorithm for training process. This is the entire steps. The first, we have to pre-process the data, then convert data into vector format. Then we have to find out CL values. Then after selection parameters, we have to identify, then prediction parameters. Then after that, predict the labels by using rule-based approach. Then we have to find the accuracy, then precision, recall, and F1 score. This is the algorithm used for training process. Then here in our study, we used two data sets. One is sentiment tweets, other one is restaurant reviews. In sentiment tweets, there are around 10K, more than 10K tweets are there. And in restaurant reviews, 1001K reviews. And the accuracy what we got here, it is for sentiment tweets it's 92%, and for restaurant review it is 81%. Because restaurant review has only 1000 reviews are there, for sentiment tweet it is 10,000 reviews. And precision also 95 and 63, 94, 80, then 95 and 70. These are the two data sets what we used for analyzing the performance of the developed machine learning model. Then the comparative analysis also done with the papers, but there is no exact papers. But here 3 papers are selected based on the Twitter data. For first one is they used semantic analysis with the word net. Another one, in the second paper, they used a decision tree algorithm, and the third one is deep learning algorithm. And the accuracy level also given, and the proposed model is 92% when compared with all these. And for restaurant review also, we selected 3 papers and we compared the accuracy level, precision, recall, and F1 score. The proposed model is performing better than the existing ones. So conclusion of the paper, we used Cellular Automata based approach. So we didn't use any pre-trained word embeddings or word dictionaries. And the entire thing is relies on CL signals, circle length values. and further improvement is required. I'm thinking that if we accumulate more reviews in the data set and data set size will be increased, then the performance also increased. And the future work, we want, what we done here, it is the binary classification. So multi-class classification, then multilingual sentiment analysis, that also want to do in future, and enhance accuracy and F1 score of the model. These are the certain papers that we referred for the work. Thank you.
Thank you. Thank you, Elizabeth, for the nice presentation. Now we can take maybe one or two questions from the audience.
Hello, Elizabeth.
Yes.
Yes, ma'am.
It was a nice presentation. Actually, I have seen that you have processed the natural language and you have used cellular automata by converting each letter into ASCII codes, right?
Yes, ma'am.
So, have you used any image for doing the same?
No, ma'am. Actually, we are considering only text-based analysis. No visuals and
And
no speech.
yeah, in text-based analysis also there is another thing that sometimes you say something that is a positive sentence, but actually it means something negative. So, have you used this kind of thing to analyze the sentiment?
So we used, ma'am, data set, and we used labeled data set. Already the class labels are assigned in that. So we applied that data set for
In
developing.
your data set, was
Yeah.
there any this type of sentence that actually that is a positive sentence, like say congratulations you are in hell? Actually it means something negative, but it is a positive sentence because you are starting with congratulations and something. So can you identify this sentence as negative sentence? The sentiment is negative actually.
In some cases, there is some kind of problems are there. That is why that accuracy level is little less now.
Okay, okay, thank you, thank you.
Okay.
So I have a query here.
Yes, ma'am. Yes, sir.
So how the mapping in between the sky value and the CA rule is taking place?
Sir, the length of the CA is same as the length of the text. That means if a text contains number of characters 50, then that CA also contains 50 cells.
Okay. And what about the rules, the mapping of the sky value of a character and a particular CA rule invoked?
Yeah, yes, sir. This ASCII value of that particular cell is acting as a rule in the CA for
But
that
then,
particular cell.
yes, I understood. But then the rule, but the sky value varies from 0 to 127 and varies, the rules varies from 0 to
Yeah, we
256.
used a table-like structure, sir. In that, all the letters and corresponding ASCII values are already defined. Total 127 ASCII values are used here, and all the special characters and special symbols are removed during pre-processing time.
Okay, I understood. Thank you so very much. It's a nice presentation. Thank you.
Thank you, sir.
Okay, so let us thank the author once again. Thank you, Elizabeth.
Thank you, ma'am.
Thank you.
Thank you.
So the next paper is Cellular Automata with a large cycle generator. I call upon stage the authors, the presenter, please. This one, right? This is yours.
This one. Good afternoon, everyone. Today I'm going to talk on cellular automata with large cycle generator. Myself, Sukanya Mukherjee, and my co-author is Sumit Adak. In today's topic, our objective is to figure out such cellular automaton of size n which can produce a cycle of given length L. Now, question is, that's our objective. Is it feasible practically? So, first we have to understand here L, that is the cycle length, is finite. So, we have to use finite CA, that means CA consisting of finite number of cells. And to get such objective, definitely the CA will be influenced by the local rules and the arrangement of local rules, which leads to think us we have to use non-uniform CA. Now, to get a maximum possible cycle length for an n-cell non-uniform CA, we have to intelligently arrange the rules, which is actually challenging. So, for our objective, that means if we want to design a CA of size n which can produce n-length cycle, so we can start with this. Definitely the best solution is minimum size CA that generates a cycle of the particular length. So what we try to say, if L is the length, okay, and n is the size of the CA, the relation should be like this, log base 12 plus 1. Now, question comes, is it practically possible? Yes, there is a concept of maximal length CA where we can find the cycle of length 2 to the power n minus 1, where n is finite. Say, if we want to produce a cycle of length 31. So in that case, we can do that using 5 cells CA. Now, question comes, how we can generate such CA? There is a concept of linear CA by which we can get maximal length CA, and linear CA mainly supports the concept of matrix algebra polynomial theory. So we have to get such CA which can be mapped with primitive polynomials. Now, what is the drawback? The drawback is that the number of primitive polynomial is limited, and generating primitive polynomial is not very simple. It's time consuming, exponential. So what is our actual objective? For a given length L, which is a finite number, we want to find a binary n-cell CA which can be of size n, and n should be as small as possible. What is the meaning of this? It means it not necessarily maximal length CA, but definitely our actual objective is it should be log base 12 plus 1, but we may not get it. But the displacement, that means actual and what we are, that means expected and what we are getting, that should be the displacement should be less. Now, let's move to some basic things which required for our work. Here we use one-dimensional C of finite size, where one-dimensional C is just an array of cells, and here every cell containing two states, either 0 or 1, and the change of every cell is determined by the states of that cell and its neighbors. As here we are using three neighborhood architecture, so here the change of cell is determined by that cell and its left and right neighbor. Here we use null boundary CA, and the CA can be linear and non-linear, and the CA is non-uniform. So if 0, 1, 1, 1, 0, 1, 1, 0, if we look at this, it's a configuration. That means collection of state values of all cells at time t. So the next time we get 0, 0, 0, 0 by the help of CA, we can call it as non-uniform CA, where the rules are 90, 150, 45, and 65. So we can categorize like we can say like this. Actually, on every cell we are using the local functions or local rules, which we identified represented as f0, f1, f2, f3, and the arguments are actually here. F are the functions and the arguments are the state values, state values for the given cell and its left and right neighbors. This is a concept of this is a cyclic space, this is a configuration space where 0110 is actually non-reachable and 1111 is cycle. Now it is another thing that is here. You look at the diagram, all states are actually connected. Connected in that sense, actually they are in some loop, and that's why they are called as cyclic states or cyclic configurations. Now, next we represent the concept of cycle structure. Cycle structure means how many cycles and what is the length. According to the length, how many cycles the CA have. So here we can find the CA is 4-cell CA and it has 30 length cycle and 1 length cycle. So definitely the cycle structure will be 1, 3. 1, 3 signifies 1 is the number of cycle, 3 is the cycle length, and 1, 13 signifies 1 is the number of cycle and 13 is the cycle length. Here for our CA model, we use reversible CA. Here actually we use ECA and the CA is non-uniform and reversible. Now, actually, our objective is what? For given cycle length L, using n-size CA, we want to find a solution. For that, what we are trying to do, we actually concatenating the CAs. So here you can see F and G, these two are function which are actually CAs of 4 cells and 3 cells respectively, and we want to concatenate these CAs. And here X, capital X is representing a cycle of 4 cell CA, and capital Y is representing a cycle of 3 cell CA. So what is Z? Z is actually the cycle produced by X. How we are doing this? By the method of LCM. That means, say, let's consider if I just pick up first element of X, 1,000. After that, we are concatenating the first element of Y, 000. What will be the next configuration of 1,000 and then 000? Definitely, the first part that I pointed out as red color, that is taken from the X, that is the second element of X, and 111 is the second element of Y. In this way, you can understand one thing: the elements of X will be repeated after multiple of 3, and as the length of the cycle Y is actually 7, so total cycle length which will be generated by XY is 21. That is the LCM of the value, the length of X and length of Y. Now, how do we actually get the corresponding CA? Just try to see from here. Here we are using 7-bit representation because total length of the CA will be 7. You can find from here, if at cell 4, if we find 1, okay, then also we are getting, in cell 3 we are finding 0, we are getting 1, and in cell 4, if we write 1, we are getting 1, and in next case, if we write 0 in cell 4, then also we are getting 1. So what does it mean actually? The next state of cell 3 is independent of cell 4 for any configuration. That means any change occurred in cell 4 will not actually affecting cell 3. Similarly, here also we can represent the concept of next state of cell 4 is independent of cell 3 for any configuration. So this type of things is called as right independent, and this is left independence. So from here we actually get the resultant CA. Here actually we are concatenating CA1 and CA2, and ultimately we will find this final CA 9, 150, 45, 195, 85, 105, 20. Now please try to see from here, the last cell of first CA, that is cell 4 cell CA, was 65, which is replaced by 195, because we have designed in such a manner. If we look at 65, we can break the structure of rule 65, and we actually consider if the combination 000 and 001, both of them having the same value for 65. So when 195 rule is selected, before that I have written this as R3. R3 means R0 is 9, R1 is 150, R2 is 45, and R3 should be 9. But how do I get 195? So R3 000 and R3 001, both of them containing the 000, this nested combination of 65, which is 1. So in this way I get 195. And how do I get 85? By the help of 5, where 000 for R4 and 100 for R4 having the same value for 000 for rule 5. Now question comes, just using this way we get the large length cycle, or just why I am saying large length, because you can understand for n cell CA, if it generates nearest to maximal length CA, so obviously it's a large length cycle. So is it possible? No. What we need to consider, for every what CA we are concatenating, for every CA we have to maintain some property. That means we only select those CAs which are actually following this property. This property is what? If n1 is the CA size, then it can produce 2 to the power n minus 1. It's not maximal length CA, it is 2 to the power n minus 1. That means if n1 is 4, so it can produce 8, 9, this cycle lengths. Okay, it's not mandatorily 15 cycle lengths. So how we get it? Actually we calculate this work already published. So here we take the help of this work. So we calculated the right neighborhood dependency of the rules. Next we calculated the left neighborhood dependency, and after that we use a parameter P, and based on the P parameter, which actually representing the right neighborhood and left neighborhood dependency, and we categorize the rules into 4 categories: completely, partially dependent, weakly dependent, and independent. So what is the importance of this? Let's move to strategy 1. Here I want to tell you, we are actually taking the rules, component CA rules, maximum for completely dependent, next level partially dependent, and very less for weakly dependent, and we are not taking from independent. So strategy 1 says what? If L is my target, L is my length, so what we will do, we actually first categorize, say CA size 4 to CA size 30 I want to take. So I arbitrarily choose any a random number is generated for CA size. For that CA size, a cycle length will be taken. After that cycle length, let's consider L1 is the longest cycle length for N1 cell CA. Longest cycle length means what? It is 2 to the power n, it is greater than 2 to the power n minus 1. We check this L1 equals to L or greater than L? No. Then we generate L2 in the same manner and do the LCM. So what will happen? Until we are getting L or greater than L, we are continuing. And definitely, which is the best solution? The best solution is log, which is nearest to log base to L plus 1. Now, what is the drawback? See, every time I am selecting a random, I am selecting a CA, it may happen how actually we are generating, I just told you we are giving more priority on completely dependent, then partially dependent, and weakly dependent. So in this way, even if we try to generate, it may happen I am not getting the longest cycle for that particular long cycle for that particular given CA. So every time I am changing and trying to generate, so what will happen? It is very time consuming, and second, it's not guaranteed I will get large length cycle using that operator. So what is the solution? Solution is that we will do some pre-computation. So pre-computation of cycle structure. So if for every particular CA size, we keep the information. So let's consider for CSIs NJ, we find out all possible, we find out all possible large cycle lengths. Large cycle lengths means which is greater than 2 to the power n minus 1. So next is our strategy 2. So what we will do here, also we select any number from 3 to 30, and we select n1. So after n1 is what? N1 size component CA we have to generate. How can we generate? Here we actually choose random with Gaussian distribution. We are randomly choosing with more weights on generating longer cycle. So what will happen? We process the same thing until we get the best solution. So if we look at this result, yes, we can find out the solution, but definitely it's very if you look at the displacement means what you expect, say for 2 to the power 500 to 2 to the power 501, what you are expecting, say suppose just using 501 bit you can solve it, but it needs 509. So in this way we have shown the results. Next, to get rid of from this problem, actually we are taking the help of evolutionary strategy. Here we are not directly using the genetic algorithm, we are taking some help of genetic algorithm, but definitely some variation is there. First we randomly generate the candidate CS. Next we compute the displacement percentage, generate offspring just using selection and mixing of significant features. So I try to use here the concept. First, randomly generate the component CS, and from component CS we find the candidate CS, and it may happen the candidate CS not giving good solution. Good solution in that case, the fitness score is not good. Fitness score means what? The CS size. After that, what we do here, we actually figure out what are my significant features. Now, when we find out significant features, how do I figure out significant features? From the initial population, we take the component CS, and definitely the component CS are, when the component CS are taken, we actually find out the cycle length and its factors. What is our objective in LCM? Why we are getting the bad results previously or not good results? I should say I am not doing the concatenation of those CS where the cycle lengths are co-prime. If we anyhow can find the co-prime cycle lengths and do the LCM, definitely we can get better solution. So keep this thing in our mind. Actually, this is the concept of significant features. So you can see candidate C1 to candidate CJ randomly generated. After that, this is called as elementary component space. So we have taken every one of the component here, K1, K2, Kp, Kj, all are the longest cycles. And here actually offspring is generated. Please all of you look here. Offspring is generated here not by the help of two parents. Here from multiple parents. So what we are taking the good features from the different parents, and then we are generating the offspring. So here first randomly generated, then we evaluate the score, then ascending order we sort them. Next best 30% we are taking, 50% we do just the mixing means good features from multiple parents, and 20% randomly with uniform distribution. That's the impurity we are adding. Keeping this thing in our mind, we can get better solution, and we just continue these steps until we are getting two successive steps giving same type of results. So these are the significance of mixing and randomness. This is my results. Thank you.
The last paper for this session is titled A Cellular Automata-Based Approach on Assessment of Thickness of Stratified Mineral Deposits. May I please call on stage the presenter? Online? Remote presenter?
Good afternoon, everyone. My name is Supreeti Kamilya. I am going to present our paper, A Cellular Automata-Based Approach on Assessment of Thickness of Stratified Mineral Deposits. My co-authors are Soumyadeep Paty and Sumit Adak. Now, actually, as we can see, we will assess the thickness of stratified mineral deposit. This means basically it is an interdisciplinary work between mining industry and our computer science. So here, stratified mineral deposit is actually a type of deposit that actually form as a layer. So our target is to find out an alternative way. Why alternative way? Because there are some traditional methods to estimate the thickness of stratified deposits, but we have this our tool, Cellular Automata, to assess the thickness of the stratified mineral deposits. So we find an alternate way to assess the thickness of the mineral deposit. And for that, we have used two-dimensional cellular automata. It is a finite C we have used. Some traditional methods are inverse distance interpolation method and inverse square distance interpolation method, which we have used as the transition function of the CA. The proposed method provides identical results as of the traditional methods, however, in more simpler and efficient way. Now, what is actually mining of minerals? Mining, all we can understand that extracting the minerals or materials from the earth crust, what we have needed. So, minerals are actually deposited in various forms, sometimes in large mass, sometimes it vertically occurred deposit of metal, sometimes it is in terms of stratified deposit of coal, that is in layers, or placer deposit like randomly occurred deposits. So it is important to find out the properties of different types of deposits from the earth crust. It is an important task in terms of economics of a nation also. In this work, we deal with the coal seam, that is stratified mineral deposit, and from the deposit, coal is extracted. Now, we will see how the mineral deposits are formed. It is formed in two ways. One is sedimentary deposit, another one is igneous deposit. In sedimentary deposit, actually it is created by air or water that carries the sediments and deposit it. And it is found in layer by layer, and these layers are known as strata, and the deposits are known as stratified deposit. For example, coal is a stratified deposit, and the strata of a coal is known as coal seam. Another type of deposit is the igneous deposit, that is actually created by solidification and cooling of magma. An example of igneous deposit is deposit of gold. Now we see the thickness of coal seam. See, we can observe two pictures. The left picture is of the layer of coal that has been taken from far away from a rock. The black colored shown the coal layers, the coal seam layers. Now, at the right side, we can see that in a layer also, the thickness varies. It becomes thicker to thinner in a layer. So it varies widely depending on the geological formation and location, and can range from a few centimeters to tens of meters, and can impact the efficiency and cost effectiveness of mining operations. Obviously, uh, if we take some portion of the coal seam from a mineral while mining, if we get thicker version of the coal, obviously it will be economically viable because we are getting much and much amount of coal from there. Thicker coal seams are generally more economically viable for mining compared to the thinner seams. Now, what is the motivation of doing this work? Why do we actually need this type of assessment or this type of estimation? See, the traditional method is you do some boreholes from the earth crust to understand the thickness. What is borehole? That you are kind of drilling the earth crust and you are taking some portion of the coal, and from that you just find out the width of the portion. This means you are estimating the thickness, not estimating, actually you can properly calculate the thickness in from the borehole. Okay, the right side figure shows the boreholes actually, but it is not possible to drill the boreholes in hundreds and thousands of amounts, right? That is why we can only drill a few number of boreholes, because doing many number of boreholes will be very much costly affair. That is why we need to do some boreholes, and we have measured the thickness of in some portions, some geological portions, and from that portion you need to estimate the thickness of the coal seam from other portions, right? So, accurate coal seam thickness estimation enables efficient planning and operation of mining activities, and it leads to more effective use of resources and increased profitability. Why? Because as I said, that more number of coal means more economically beneficial, and it determines the quantity of coal deposits, as we can determine the thickness of coal in some particular geometrical area, and it can aid in identifying areas of potential coal reserves. Now, the thickness of coal seam is considered as a spatial data, where every data value is connected to a spatial location. Obviously, because the layer is not same everywhere. It varies from few centimeter to few meters, as I said. That is why it is obviously geometrically dependent, and it is spatial dependent. So, known thickness values carry information of the unknown ones. That is why from the borehole data, we can understand the known thickness. We come to know the known thickness. And from this known thickness, by using interpolation method, we calculate or we estimate the thickness of the unknown point. So the one traditional method is inverse distance weighting method, by which we can assess the thickness from the known borehole points. So it is a geostatistical method used to estimate the value of a variable at an unsampled location based on the values at surrounding sample locations. And it assumes that the influence of a data point on an unsampled location is inversely proportional to the distance. The calculation is much simpler, but the problem is that if we have a very complex type of geometrical geographical structure, in that case it would be difficult to estimate the thickness by using inverse distance weighting method. So let us see, suppose x1, x2 and x3, these three are actually the known borehole points where we would know the thickness. And based on these 3 points, we need to calculate the thickness of the point x. How I will calculate it? Using inverse distance weighting, we'll calculate it by calculation will be done as u1 by d1 plus u2 by d2 plus u3 by d3 divided by 1 by d1 plus 1 by d2 plus 1 by d3, where u is the thickness of point x. Now, another method is inverse square distance weighting method, where we have applied the square of the distance between the points, unlike the inverse distance weighting method. Why we are using this? Even though inverse distance weighting method was much simpler, but it was unable to estimate every time the complex geographical areas, geographical structures. The steep gradients, in case of the steep gradients, it becomes difficult. It becomes difficult to estimate the thickness. But here, in case of inverse square distance method, as we are assigning more weight to the nearby data, it is possible for us to calculate the thickness even in more complex geographical areas. So now how we will estimate by using this method? Here again, x1, x2, x3 are the known points and x is the unknown point. So we will calculate it as u1 by d1 square plus u2 by d2 square plus u3 by d3 square divided by 1 by d1 square plus 1 by d2 square plus 1 by d3 square. So by which we can calculate this. However, it is computationally intensive compared to the previous method. So what is the trade-off between these two? How we can get an efficient way of finding the thickness of an unknown point by knowing some of the known points, because it is not possible to know all the known points by doing this borehole technique. That is, so IDW, that is inverse distance weighting method, is simple, but it is unable to estimate steep gradients. Whereas in case of ISDW method, it able to estimate the thickness, but it is computationally intensive. We have seen that using cellular automata estimates the thickness properly. It gives the same result as given by these two previous methods, but in much faster and efficient way. Now, we may not need to define cellular automata properly because my friends have already told it, but just let me briefly introduce it. That cellular automata is basically consists of different cells that changes its state depending on some function, right? And a configuration, the collection of the states basically is called the configuration. Here we have used two-dimensional CAs where it follows the moon neighborhood. Moon neighborhood means from a state we will consider its north, south, east, west cell as well as the orthogonal cells. So the features of CA what we have used in the study are a two-dimensional CA with moon neighborhood, and it is a finite CA. It will be a null boundary CA, and the states of the CA can be between 0 and 100. The transition function we used here are the inverse distance weighting method function and inverse distance squared weighting function. So U is 1 by C, summation of I equals to 1 to 8. 8 is because we have used the moon neighborhood. Xi divided by di to the power p. The value of p is 1 for inverse distance weighting, 2 for inverse square distance weighting. The data we have used here is taken from a part of eastern India, which is located in Raniganj coalfield. There are 12 to 15 boreholes per square kilometers, and total 54 borehole data are used to estimate the thickness. A portion of coal seam of size 2000 meter in north-south and 1800 meters in east-west direction is considered in the study. And the portion is divided into 25 by 25 square grids. That means 2000 by 25 is 80 and 1800 by 25 is 72. 80 by 72 size C we have taken here. The thickness is assumed at the center of each grid and it remains constant throughout the same grid. This means, suppose in this picture we can see that X is the point and the other points are X1 to X8. So the thickness we are considering at the point of each grid, each small squared grid, and all the other points will be constant in the same small grid. So the point X at cell 0, 0 and the other points are X1 to X8, and the thickness of point Xi is considered as Ui. Di is the distance from X to Xi. Now we will calculate the thickness of point X as U equals to, we will use the same transition function. And how we will calculate the value of C? The value C will be calculated as C equals to summation of I equals to 1 to 8, 1 by di to the power p. For inverse distance weighting, C is calculated as 6.83, and for inverse square distance weighting, C is calculated as 6. Now, The initial configuration of the CA is all the thickness values of the collected data. That is the borehole data basically. And if we do not, if in some places we do not have the data, we will put 0 in these places. In the next steps of transition, the state of the cells may be changed from 0 to some other grade value by which we can estimate the thickness. See here, suppose we have this portion of coal seam and we have some of the data that were calculated from the borehole. Okay, now from this calculated data, we have used, by using the transition function of inverse distance weighting, we can, inverse square distance weighting, we have obtained these values as the thickness of the unknown points. And finally, after some evolution, we get all these points, and we now know all the thickness of all the unknown points from the known points. Now we get the bar diagram and surface plot for the same, where we can see the thickness of the coal seam in the northeast area, and it has been calculated for the inverse square distance method, where we have assigned the weights to each thickness, each distance. Now to conclude, we can say that the present work focuses on estimating the coal seam thickness using two-dimensional cellular automata, where we have used the moon neighborhood CA. The inverse distance and inverse square distance functions have been used. Even though it has given the same result, basically we should get the same results because the thickness is basically same, but it is much efficient way, because it becomes very much faster to evolve and get all the values in the same grid. The study suggests that the cellular automata could be used for estimating other characteristics of mineral deposits in future work. Thank you.
How did you collect the data?
The data was collected from the mining part actually. There were some coal seam actually had been collected, and they have tested in and from there they have got this from the
You were collaborating with some lab. Thank you. Any questions from the audience?
So you have said that calculating using the inverse square is computationally much more inefficient than comparing with the inverse distance. Why is that? Because I think on a computer program, calculating inverse square sums is almost as difficult. You know, how much is the computer time comparison between these two methods? Okay, and inverse distance method? So a few seconds versus. Yeah, but you know, if you have a 10% difference in time efficiency, that is hardly relevant.
We can obtain all the values at the same time. So we have actually shown that we can use cellular automata, we can apply cellular automata to calculate all these.
No, I understand. I accept that point. I'm just saying that when you say that it is much more inefficient to use inverse square, that is not really correct, no? Okay.
Hello. I'm just eager to know that whatever you have done here, the approaches have been followed for considering the borehole data. Instead of that, we definitely may approach for the image related data of this, the decomposition of the minerals.
Sorry, what related data?
Actually, whatever the task has been done, that cellular automata rules, everything has been applied for the data set you have considered. That is a, I mean to say that quantified data, right?
Yes, yes.
Instead of that, we may proceed for images also, I think.
Yes, because from image also you can the
Uh,
pixel, from the pixel value you may proceed, but I do not actually really
No,
work on
actually, in
that.
that case, I may need to think on that. Whatever the depositions you are talking about, there will be different images for these different decompositions, I think.
I think
So,
you can.
depending on the level of decompositions, another task can be done, maybe.
Yes, I think you can
Because
do this
actually
using image.
nowadays we are preferring the automated procedures.
Yes.
So if we are going for that, every time we need to collect the borehole data. For that, manual intervention is definitely required to get that data. Whereas somehow automatically or by robot or something else, we can grab the photo or image of that, so we can process on that and
Yes,
easily.
but for a large geometrical area, you cannot always get the image of all the portions from the geometrical areas, and the thickness varies. I mean, varies from very thin to very thick. So, from which area we will collect the image and test? That is the question. That with wide area range of the geometrical area, you cannot collect the image of the coal seam from each and every area and check. That is why we have taken some borehole data from here and there, and then based on these data we have interpolated and calculated the point, the data from the unknown point, data of
Yeah,
the unknown point.
of course. If we are going for that borehole data, then definitely we are getting the chemical information of that, which is
Yes.
much more appropriate. Definitely,
Yes.
wherever we are working on image, in that.
I think you can work on image, but for that you need much amount of data. I mean, numerous images you may
Yes,
have to
maybe
collect.
cases will be there, and definitely we may raise the questions regarding certainty of that.
Yes.
Whether in case of borehole, of course, chemical decomposition we are getting in fact. So definitely that will be much more, maybe much more effective. Whereas I think alternative can
Yeah,
also
you
be.
can proceed with image data also
No,
to
I'm
and
just
check
asking.
whether
Yeah, whether
what will
it
be
is
the
possible
accuracy.
to go with that also. Or not.
Yes, 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 it is possible. I think.
Thank you.
Okay, so we can thank the author now. Online, from our audience who have joined remotely, is there any question? I don't think so. So let us thank the author once more.
So, on behalf of organizing committee, we appreciate Dr. Naskar for conducting this session nicely and smoothly. So, from the organizing committee, we are presenting this memento to Dr. Naskar.
Thanks to all the audience and authors and delegates present here and who have joined remotely. With this ending the day 1 of ASCAT 2023, we shall assemble here tomorrow morning at 9:30 a.m. Till then, goodbye, have a nice time, and thank you for attending once again. Thank you.